So I'll share my page. I'm going to go to the back of the book and we'll do the chapter review. So let's see the e-text. And we're working on 16 and 17. Yeah, I worked so hard to get caught up with grading for all my classes because student progress reports were due and all this stuff. So we have to grade all the assignments to make sure we can post all the stuff. And so right now I have to fill some paperwork for other things. But let's see, Batman. No, we're not gonna be looking at Batman. Yeah. So y'all remember? I think I mentioned this before that at the end of every chapter. You not only have the summary and the review for the chapter, but you also have the self-assessment quiz. So as you're preparing for the exam and you're asking yourself, what do I need to know? Versus sending me an email and asking me, what do I need to know? Because I'm not only teaching you guys chemistry, but I'm teaching you guys the skills that you need to know to survive any chemistry class, right? So you go to the chapter summary and review, and it tells you what you need to know. So in there, it will have topics that we covered, topics that are very important, topics that are key, and of course necessary for future topics. So what I'm going to do here, though, is just go with this self-assessment quiz, because I think that will keep us busy for a while. Okay. So y'all saw how I got this, right? The self-assessment quiz is in the e-textbook. So when you go to eCampus, you have to find the chapter you're working on. And the way they have the textbook over here, let's see. Oh yeah, right here. You guys have access to this, right? I found the chapter and that's how we're going to this. Okay. So here is the first one. Identify the conjugate base in the reaction shown here. So let me make sure, give me just a moment. Let me make sure everything is set up over here. Okay, hold on. Oh, I feel like I'm sharing so much stuff. Hold on a second. Let me get everything situated here. I will start sharing whenever I'm actually done with this part here. Okay, hold on. Just trying to connect my iPad. Oh, there it is. Okay. So I'll share the application again, so you guys should see my iPad in a moment. Okay. Do y'all see my iPad?
Yes.
Okay. So I'll have my iPad on here, even though I have this new chapter. Let me actually open a blank page. So I'm going to try to copy the questions here. That way we are viewing the questions as I'm able to work it out as we're working on the review. So real quick, where was that? I had a lot of things there. This one here. So this is our self-assessment quiz. So hopefully you can see both well. So I'm going to write on the right side. This is our equilibrium reaction, right? HClO2 aqueous plus water liquid, and then H3O plus aqueous plus ClO2 minus aqueous. Okay, so here we are told identify the conjugate base in the reaction shown here. So I mentioned this to you before in chapter 16 that the conjugates are all on the right, right? Conjugate base, conjugate acid, they're all on the right because they're a product of a process. When we talk about conjugate, we see the term conjugate in the context of Bronsted and Lowry acid and base. So quick recap. when we talked about the three definitions of acid and base, we started. So this is a recap right here, and then I'll come back to the question, right? Because this is a review. Recap. When we talked about acids and base, we started with the simplest definition, which was Arrhenius. Okay, and he talked about the acid having a hydrogen ion, and then the base having a hydroxide. Very simple definition, but also very restrictive, right? And then after that, that was number one. Number two, we talked about Bronsted-Lowry. Bronsted-Lowry. This is two guys working together to define the acid and the base. From Bronsted-Lowry, what we got was the acid was doing something. And what the acid was doing, let me minimize this out of the way. The acid was donating H plus, called a proton. And then the base was accepting H plus proton. So with Arrhenius, the acid possessed something. So the acid possessed this hydrogen ion. It had it in the formula. So of course, with Arrhenius, you can tell something is an acid by the fact that it possesses. So I'm going to use the term here, possesses. They don't really use this in the definition, but it has H plus, right? A base is a formula that possesses or has or contains whatever OH minus, right? So if you're looking at Arrhenius acid, you should see an H plus somewhere in the formula. If you're looking at Arrhenius base, you should see OH somewhere in the formula. If you don't see that, they can't really be an Arrhenius acid or base, right? Because they have to contain the acid ion and the base ion. Okay, with Bronsted-Lowry though, they're not really focusing on the presence or the absence of the hydrogen ion. They're focusing on the ability to do an action. And the action they're focusing on here is to donate and to accept. So a chemical that can donate a proton is an acid. So not just have a proton, but be able to donate it. And then the base has to be any chemical that has the ability to accept the proton. So they have the acid and the base have a yin and yang behavior in Bronsted-Lowry. One is the donator of the H plus, the other is the acceptor. Okay. And then number three, we looked at Lewis acid and base. Okay. Lewis is an individual. We've seen him before with the Lewis structure, right? Same guy. Lewis loves to represent electrons as dots. In Lewis's acid-base definition, Lewis says an acid is any chemical that can, this time, Lewis is talking about donating and accepting, but his focus is not the hydrogen ion. His focus is the lone pair electrons. Okay? So the acid is the chemical that can accept lone pair electrons. And then the base this time is the one that's donates the lone pair electrons. Okay, so it's all about accepting and donating for the last two groups, but what is being accepted and donated are different. Okay, so we see that here. Acid donates lone pair electrons, acids accept lone pair electrons, base donates lone pair electrons, right? So it's all about the haves and have-nots. Okay, while in the first group, or with Arrhenius, it's the possession of H plus and OH minus. Okay, so back to Bronsted-Lowry, which is what this question is asking you about. Once the acid is done donating the hydrogen ion or producing it in solution, what happens to that acid? The acid then becomes a conjugate base. So here we see in Bronsted and Lowry, the acid becomes conjugate base, okay? And then the base becomes conjugate acid after that transfer has taken place. Okay? So now that we know this, they're asking us to identify, what was the question again? The conjugate base. Where is the conjugate base? So we need to trace the acid and then see what the acid becomes. And whatever species the acid becomes, that will be our conjugate base. Okay, because we know in the product side, the acid becomes the conjugate base. So let's see. I'll start with the formula on the left, AClO2. AClO2, I'm going to track it and see what happens to it on the right. Oh, here it is. This becomes that, right? Because I can see the HClO2. On the right, I have ClO2 minus. Okay, now I have to ask myself, did AClO2, did it donate or did it donate, transfer, whatever? Did it lose an H plus? Let me see. AClO2 on the reactant side, on the product side, yeah, an H plus is missing. That means this compound here, this reactant, you can say transferred or whatever term they use, transferred the H plus because now it's missing the H plus in the product side. Because that chemical on the left transferred the H plus, then we can say this chemical is the Bronsted-Lowry acid. Because we said down here, the acid donates, or they use the term transfers or loses, whatever, donates, transfers. It's the one that's given off the H plus. Okay? And then what is the base doing? The base is accepting the H plus. So let's see over here. By default, since this left formula is Bronsted-Lowry acid, the right formula has to be a Bronsted-Lowry base, right? So how do I know it's a base? Look at what happens to it when we track the changes, right? It goes from H2O to H3O plus. It just gained or accepted the H plus. Okay? I'm kind of missing the other color page. Let me see. How do I change this color page? The paper. Yeah, I want to be able to highlight stuff. Okay, that's a lot better. Okay, so you see that, right? You see right here, this has an extra H and a plus. So it accepted it accepted the H plus. So this is a Bronsted-Lowry base. On the product side, then, this is going to be the conjugate base, and this has to be the conjugate acid. So I did all that talking just to say this is our answer here, our conjugate base. So I can go in there and see. Oh, yay, there. And you know how this review works, right? If you select the wrong answer, even if I selected the wrong answer here, it will tell you why the answer is wrong. Okay, so even the wrong answer has notes. Ideally, this is how you should take notes. When you're taking notes, you want to follow the format they have here. For every wrong answer, they have a justification of why that's wrong. I view it as being a lawyer of chemistry. You're defending your answers and defending, or you're trying to prove what is wrong and why it's wrong, and you're trying to prove what is right and why it is right. So not only is this the right answer, it's the right answer for the following reason. Okay. Any questions about that? Y'all know how this works. If you have any questions and you don't want to talk, you can feel free to type it in or whatever. So at least I can know I need to stop and address the question you have. Okay, moving on. Which pair is the Bronsted-Lowry conjugate acid-base pair? Now I've already gone through the whole conjugate acid-base pair, right? If the conjugate acid-base pair is essentially the before and the after underneath Bronsted-Lowry. Once we have defined what these are acids and bases are according to Bronsted and Lowry, you know, in Bronsted-Lowry equilibrium equations, because they tend to deal with equilibrium equations. So while we're looking at this in the overview equations, please notice most Arrhenius equations are one-way equations with the arrow looking like this, okay? As we're looking at an overview now. Bronsted-Lowry equations, most of them are Most are equilibrium equations. Not all of them are, but most of them are equilibrium equations. Okay? So let me give you guys a format of the Bronsted-Lowry equilibrium equation and what it looks like. So we have the Bronsted-Lowry acid plus the Bronsted-Lowry base. We have our equilibrium arrow, and then the acid becomes the conjugate base, and then the Bronsted-Lowry base becomes the conjugate acid. Essentially like that, right? Remember, the acid is the one that loses or transfers, whatever term they use, transfers H plus. This other one here accepts H plus, right? So when you're looking at the pair, the before and the after, the reactant and the product, those are called Bronsted-Lowry conjugate acid-base pairs. So let me try to highlight these together. The Bronsted-Lowry acid and the conjugate base, these are essentially, when I say the Bronsted-Lowry acid dash the conjugate base, this is the, how do they say, conjugate acid base pair. Okay? Like that. When you combine these two together. So I'm highlighting that. Let me use a different color to highlight the other one. The Bronsted-Lowry base and the conjugate acid is also another conjugate acid base pair. Just a reactant matched with the product it becomes after the transformation. Okay? So hopefully that kind of helps you figure things out. But then how do we select our answers? Because we have a bunch of different answer choices, right? So I told you, to go from the Bronsted-Lowry acid to the conjugate base, there has to be a loss of H plus. So H plus is what makes the difference between the acid and the conjugate base. So let me try to make this mathematical. Oh no, I erased too much. This yellow becomes that yellow. I'll just say here, the acid is losing an H plus. Okay? So I'm trying to write this mathematically. Oh, snap. I'll put that back. And then the base is gaining an H plus, like that. That's the mathematical transformation we see right here, right? The acid loses an H plus, the base gains an H plus. So the difference between the conjugates are just an H plus. So we're looking over here and seeing the first one and the second one. The difference has to be an H in the positive charge in either case, okay? So I'm looking at this and this, 1Cl, 1Cl. So back to this, right? So I'll write here, in acid base pairs, comma, the difference between the two formulas are a proton, aka H plus. That's the only difference. Okay. So when I look at my first one, for number 2, I look at ClO4 minus ClO3 minus. The difference here, I'll do it like this so we can see it. The difference here is an oxygen. So this is not an acid-base pair. It's not a conjugate acid-base pair. I let the word conjugate out here. Okay? In conjugate. It's not that. This is part A. Part B, H3O plus, I write like this, OH minus. Let's see. The difference here, I'll start with every element. I have 3 hydrogens here. I have 1 hydrogen. So it looks like I have 2 hydrogens, right? And then what else? There's a positive here. There's a negative here. if I add one positive to this one on the right, it will give me 0. So it looks like there are two positives like that. It's two hydrogens, two positives. So if you're wondering how I came up with that, let's look at the number line, okay, mathematically. Okay, this is me paraphrasing, so I really do hope it works out. It shows us that we're going from negative, so this is 0 in the middle, where 0 is a point. Actually, I shouldn't have written the vertical part. Okay, so we're going with the number line, just at this part here. 0 is a point, -1 is a point, and +1 is a point. So we have this point here, this point here. Essentially, we're going from +1 to -1. That means that each time from this to this, what are you doing? You're adding 1. Wait, sorry, we're going the other way around. Yeah, from this to this, you're losing 1. So I'm gonna go from the right to the left. I was on a roll until I had to. I'm going from this to this. From +1 to 0, you're subtracting 1. From 0 to -1, you're subtracting another 1, right? So the gap between these two is actually 2 H pluses. So I shouldn't have written it this way because that may be a little bit confusing. I meant to say there are 2 H pluses, right? H plus twice. For each step here, an H plus was lost, another H plus was lost. So how will that look if we're illustrating this? It will look like this. From H3O plus, if you subtract an H plus, what we get is H2O. That's what I mean. The first H plus lost gives us H2O. When you lose the second H plus, now we have one H left over, right? One oxygen, and the neutral compound that has a charge of 0, but the 0 is never written because it's implied. So I'm going to erase that. Now becomes negative. But this is not written like that. It's written like this, OH minus. Okay, so to go from H3O plus to OH minus, 2 H pluses have to be lost. I told you guys the difference between the two formulas is just 1 H plus. When I said a proton, I meant 1 H plus, not 2. So that's what invalidates. Don't skim over your answer and be like, well, okay, yeah, this one here. Go through, okay? Where was I? C, NH3 and NH4. Okay, let me see. Going from NH3 to NH4, I guess I can write it this way, plus. I see that we have an additional H. You can see that. An additional positive. So, okay. But so the difference between these two is an H plus. So I think the answer is C, but just to check, HCl, HBr. Wait a minute. They have the same number of H's. So for sure, my answer is the third one. The acid and conjugate base pair differ by H plus. Oh, they had the same formatting issue right here, y'all. Listen, they had to make this stuff accessible at some point. They used to have these answers here, right? But when they went back to fix it to make it more accessible, somewhere in their formatting, they end up with this E symbol when they're writing equilibrium arrows. So just translate that weird E symbol there to be an equilibrium arrow, and then it works. Okay, they're asking you number 3. Any questions about what I've gone over so far? The difference between the acid-base conjugate pair is the H plus, okay? So we're moving on to number 3. Number 3, we're told, which acid has the largest Ka? Ooh, we're comparing acids. So largest Ka is what we're looking for. And then you see how conveniently they haven't given you the Ka? Okay, we have HClO2 versus HBrO2 versus HCl. HIO2. Okay, so HClO2, HBrO2, HIO2. You know what I realized? I realized I'm answering all the questions. The review should be a two-way thing, right? So, what do y'all think? Which
We're
one do you?
waiting for you to say something, or you're gonna
I'm
answer.
sorry. I told you I'm sorry. Okay, my
It's
bad.
gonna be HIO2.
Huh. Okay. Because for this one here, I did want to let me see what Rocio said. Okay, let's see. For this one here, when you're looking at Ka, there's a lot of things we have to combine, right? So let me show you why I'm about to go back to the chapter. First of all, we look
Oh,
at
I'm
these.
sorry. It's HCIO. I'm sorry.
Which one? HClO2?
HCIO. Yeah.
HClO2? Okay.
Yes.
So when you list these, you have HClO2. If you look at the group arrangement in the periodic table, where's my periodic table? Right here, we have F for group 7, right? In group 7, we have F, we have Cl, we have Br, we have I, right? And so at some point during the PowerPoint, you looked at comparing binary acids, right? Versus comparing oxy acids. So with this question here, even though it looks pretty harmless, what you want to look at is this. Number one, you want to judge the kind of acids you have. So let me go ahead and go back to the chapter 16 because the question they're asking you is not as simple as it appears. Here's the thing with chemistry, right? The question has a few words. You're thinking if it's few words, it's simple. No, it's not. It's not. So let me go ahead and pull this out. They're asking you Ka, but we're looking at acids, right? This is one acid, second acid, third acid. These are all oxy acids. So these are oxy acids, right? How do I know that? They all have oxygens, oxygens, oxygens. And their acidity doesn't, the difference in the acidity has nothing to do with the oxygens, because hopefully you can see they all have the same number of oxygens. The first one has two, the second one has two, the last one has two. That's not what's different. What about hydrogen? So I'll say here, let me list the things I observe. I observe they all have same number of oxygen, right? Because sometimes one of the obvious differences the in the formula, the acid formula is the number of oxygen. And in the past we have said, or in the PowerPoint, more oxygen, more acidic, right? But the oxygens are same. What's the next thing? Hydrogen, they all have the same number of hydrogen. Once again, we're doing a lot more of this arguing and trying to defend our point in 1412 than we ever did in 1411, right? 1412 is a higher level class, and they're teaching you that skill of being able to prove your answers and not just say, well, it is because, right? Remember, I went over this part here. Okay, let me fast forward to oxy acids. Yeah, here we have binary, okay? So what I'm going to do real quick here, because we're very close to what I'm trying to say, the quick recap. If we were dealing with binary acids, and these are our group 7 binary acids, we'll just say, what was the bottom line? As you go down the group 7, the acid gets stronger, right? So down the group, you have a very strong acid. That's what they're saying here. Binary acid strength increases down the group. But we're not dealing with binary acid because we have the ones with the oxygen. The ones with the oxygen tend to have an opposite trend, but I want you guys to see where that is in the periodic table. So they're showing you here. These are oxy acids. So many words. Oops. I think I skipped by quite a bit. Oh, these are oxy acids. And then this is the line that we're looking for. Acidity of oxy acids decreases down the group. So that's an opposite trend to what we just saw, right? So yeah, so Jacob, you got it right the second time around, but this is the PowerPoint I wanted you guys to see. Acidity of oxy acids decreases down the group. So when you line these up to match the group, HClO2, HBrO2, HiO2. This is going to be the most acidic. Okay, good. So we're going to go with that, most acidic. But they didn't really ask us about acidity, did they? No, they asked us about Ka. So the other question you have to ask yourself, once you've decided what is the most acidic, what has acidity got to do with Ka? Okay. So before I give you the answer, I know it's like, just give us the answer already. No, I'm supposed to show you how to get this answer, y'all. Let me go back to the slide. What slide was I on? 14, where it talks about Ka and acidity. It's somewhere here in these numerous slides. Hold on. I feel like we're getting closer. Okay, this is where we mentioned the Ka value. But I want to get the PowerPoint slide where it actually mentions it, Ka and acidity. Does it ever get to it? Yeah, so it's somewhere here where it does mention. So I'm just going to give you the bottom line because I'm already like, oh my goodness, where do I find this? The larger the Ka, the larger the more acidic the acid is. Okay? So the larger the Ka, the stronger the acid. It should say that somewhere in here. I'm just not seeing it right now. Maybe I skipped over it. It must have been that one slide. Anyway, larger Ka means stronger acid. Okay, so we have said that HClO2 is the most acidic. So by default, this should have the highest Ka. Okay. Of course, now if they gave you the Ka value, just go by the Ka value, right? But they didn't give you the Ka value. So let's see. We hope this is correct. Wait, I clicked the wrong. I clicked the wrong. What am I doing? I just, I just.
That's what got me because I said the H as I was thinking about HCIL and I just saw the IO.
No. Like I just said HClO2, but I'm looking over here and clicking the first one. My eyes were focused on my iPad as I was clicking. So I'm like, what? Why did I click the wrong one? But yeah, it's this one here. And so they tell you for oxy acid. So you see how they think? They say for oxy acids. So you want to train your brain to think that way. I know it's kind of a different way. It seems tedious, but this is a training. They want you to relate the formulas. Like they pick those formulas for a reason, and you have to be thinking of the reason versus going to Google. Yeah, you could go online and Google the Ka for the first one, Ka for the second one, Ka for the third one, and then pick the strongest one. But then you miss the whole point of what you're supposed to be learning here. You're supposed to be learning to think like this. First of all, judge these as oxy acid because they have oxygen here, here, here. You're learning observing skills, right? Like, okay, why do they all have the same number of oxygens? Why do they all have the same number of hydrogens, right? And we're told here the acid strength increases with increasing electronegativity of the central atom that's bonded to the oxygens. And they show you all the stuff, right? So if the chlorous acid is the strongest acid, it will therefore have the largest Ka. So they kind of combined two rules in there. Strongest acid, largest Ka, and then the order of increasing acids when you have oxy acids, increasing acidity. Okay. And then you also recognizing this is an oxy acid, not a binary acid. Okay. And so let's see, identify the strongest conjugate base. With this number 4, I didn't go into this other detail because normally I don't cover this part on campus just because of time. And so I will skip over this for right now. Okay, this one here. What is the OH minus concentration in the aqueous solution at 25 degrees where you have H3O plus concentration being this? Okay. So now we're kind of going into details of chapter 16, right? They gave you the temperature on purpose. This part here is significant. And once again, you're like, well, when do you know the temperature is significant and when it's not? When you're reading questions, you have to notice things. Be like, I want to say Inspector Gadget. Be like an investigator. Why are they asking you these questions? Why are they including this number? Is this number important? When you're passively reading the questions, passively going through the motion, you're missing what they're trying to get you to do, which is to be suspicious, not to like think everything is a conspiracy. No, not to that level of suspicion, but they want you to be actively, why is this number significant? So the temperature of 25 degrees Celsius is significant just because to look at the relationship between OH minus and H3O plus, you need to look at a formula, right? So we're asking you, what is OH minus? Remember, these brackets are concentration bracket. That means that whatever number you get here, the unit has to be molar. And if you look on the left, all the answers, the units are molar, right? So what is the concentration? I didn't want to write the word concentration, so I use the symbol of an aqueous solution. Okay, some solution, aqueous, hint, hint. And then we're given H3O plus concentration as 1.9 times 10 power negative 9 molar. So this other concentration is given, and my temperature is given to me as 25 degrees Celsius. So before I continue, does any of you know the relationship between OH minus concentration and H3O plus concentration, hydroxide and hydronium concentration in the formula? Oh, this is the wrong class. Did I close my PowerPoint? I guess I did. Okay. So it is Kw is equal to H3O plus times OH minus. Okay. And then the Kw here has a specific value when the temperature is 25 degrees Celsius. That's why they included that in there. Because if the temperature is different, the value of kW is different also. We have only learned about one kW, and that kW is only valid at that temperature. It's those low-key things that people in chemistry communicate, and you're like, is this important? In the world of chemistry, it's important because there's a whole table out there somewhere, not in your textbook, where there's a bunch of different kWs at different temperatures. So if somebody from that side having that huge table is approaching this question, their question will be, well, which kW do I use? You didn't specify the temperature, right? I mean, they'll call somebody. So kW is a constant at this temperature. It's 1.0 times 10 power negative 14. Okay, so I thought I downloaded. I guess I deleted after I downloaded my PowerPoint. Or is it still open over here? Nope, that's my 1411 one. Yes, I'm going to go ahead and highlight this in the PowerPoint because I am trying to show you how these questions relate to the concepts we have covered. And so, yeah. So if we know what this number is, and we know what this number is, can we now solve for this number? Yeah, it's a simple mathematical rearrangement. Then we can solve for hydroxide. Okay, so let me open this one. Yeah, there's a lot of slides here, but as you're going through the chapter, it helps for you to summarize the chapter, right? Okay, let me see. Oh yeah, hey, acid-base conjugate pair over there. Haha. Let me see. I am looking for the hydroxide. Yeah, the Ka thing I was talking about earlier. There it is. I'm looking for, this is it, right? Yeah. There it is. You see that formula right there? There. So Kw 1.0, well, they have 1.00 times 10 power negative 14 at 25 degrees Celsius. It's a different number when the temperature is different, right? So to solve for OH minus, just divide by H3O plus. Both sides divide by H3O plus. And we get OH minus equal kW, which is going to be 1.00 times 10 power negative 10 over 1.9 times 10 power negative 9. Don't forget to use parentheses. Calculators could not care less about your parentheses, but when you use parentheses with scientific notation, the calculator interprets the number correctly. So open parentheses, 1 exponent negative 14 to the right, close parentheses, divide by, open parentheses, 1.9. Oh, I said 9 and I typed 8. 9 exponent negative 9 to the right, close parentheses. Let's see what I get. Okay, so for my OH minus, what I'm getting is 5.263. Okay, hold on a second. 1, 2, 3, 4, 5, 6. Like I should probably set my calculated scientific notation, but this is what happens, right? I teach different kind of classes. In some places, I just need the number in standard form. So could I? Yeah. Do I? No, because I need my calculator for so many different reasons. Oh, I need to go back to the self-assessment, right? Okay. My answer matches this the most, right? So let me check. I hope it's right. Oh, look at that there. So yeah, they use the same formula once again. Let me see. How many more questions do I have? Okay. Next one. A nitric acid solution has a pH of 1.75. What is the molar concentration of HNO3 aqueous solution? Okay. Number 6. HNO3 aqueous. We know it's an acid, and they gave us its pH as 1.75. Okay. They're asking you what is the molar concentration. So they're asking you what is the concentration of HNO3, right? And when they say molar concentration, they mean in molarity. And if you look at your answer, all the answers are in molarity. When I was a student, because I wasn't very comfortable with everything, I mean, I didn't have a lot of experience, right, in all of this stuff. So my question was always, okay, see you. Yeah, my question was always, what's the units? Are they asking for moles? Are they asking for molarity? So if it was a multiple choice, which we didn't have a lot of that in our homework assignments, we had a lot of, fill in the blanks. No, but sorry, excuse me. We didn't have fill in the blanks. I'd never seen fill in the blanks exams until I got to America. I'm like, what is this? We had a lot of paragraph, like show your work. Here's a line of a question, and then you have a whole page, 2 pages, show your work until you're tired and you give up. Okay, so I was always needing that units. So here's the acid, here's the pH, find the concentration. Okay, here's the deal. We have to judge our acid, right? What kind of acid do we have? Because the kind of acid we have determines the kind of approach we'll pick. So I'm going to judge my acid and I say, this is HNO3 is one of the 6 strong acids. While I'm here, the 6 strong acids were HNO3, the other one was H2SO4, the other one was HClO3, HClO4, HClO4. Then we had the 3 binaries, HCl, HBr, and HI. Because I am reviewing, I am not just preparing for the questions I am seeing. So if you're wondering, why does she always detour? I actually learned this method from my friends, okay, who helped me study science better and helped me study chemistry better. Because as a student, this was in high school, as a student, if I was studying this question here, guess what I was studying? Just this question. I wasn't applying it holistically. So if I saw this question here and I was reviewing it, I wasn't applying the same concept to these other formulas. So when I got to the exam, if this formula was replaced with any of these formulas, I was like, oh, I don't know what to do. Right? So not only are we reviewing, I'm showing you how to study. Okay. Where was I? Whatever I apply here as I solve this problem applies to all of these formulas here, but for H2SO4, I will double the H3O plus, right? Because we have two hydrogens, but everything else applies equally for the rest of these, okay? So even if they switch the formula and they don't use this, but they use formula 3, 4, 5, 6, I will apply the same logic, okay? So back to the question. I was given the pH, now I have to figure out the concentration. For a strong acid, that is monoprotic, i.e., has one hydrogen ion. So I'll show you here. Let me take the HNO3, and then for this one here, I'll go ahead and I will add it to water. Add it to water, and then I'll use my one-way arrow to show you what happens. This is monoprotic, it only has one hydrogen. When I add this to water, I get H3O plus and nitrate. Okay? So say the following applies. Okay, for a strong acid, this is a strong acid, that's monoprotic, has one hydrogen, i.e. one hydrogen ion, the following applies. The strong acid is added to water, and you see how we have the one-way arrow? This is true for the strong acid. Okay, the weak acid has a two-way arrow equilibrium. When the strong acid gets added to water, what we end up with is hydronium ion being formed, that's aqueous, and then nitrate ion in this case being formed, that's aqueous. The reactants cease to exist. Remember, strong acid ionizes 100%. That means when everything is said and done, all we have is the products in the end, okay? So what do I mean here? The concentration of the nitric acid is the same thing as the concentration of H3O plus. I did all this just to say that you see the 1 to 1 to 1 to 1 mole ratio. Whatever concentration the H3O plus is also the concentration of the acid because you have a 1 to 1 to 1 to 1 mole ratio. And we said it's 100% ionized. We also know that pH equal negative log base 10 H3O plus. From the pH, I can solve for H3O plus. Once I have the H3O plus, I can solve for the acid. Right? So they kind of fit in together as part of a big puzzle. So now that I see the connection, I can actually solve the problem. Can you solve the problem without making the connection? Yes, but it limits you on how many problems you can solve. So let's see. What was the pH again? 1.75. 1.75 is equal to negative log of H3O plus. Okay, so I have to find what this is. You can say multiply by negative 1, multiply by negative 1. This ends up being 1.75 equal, the negative and negative become positive, log of H3O plus. We have to do the inverse log, right? Inverse log is taking this number here, oops, power negative 1.75, taking this 10 power log base 10 H3O plus, and essentially this cancels out into 1. So this becomes H3O plus mathematically. I forget the name of the rule. I guess I call it logarithm rules. Now I have to do this on the left side. Take 10, raise it to the power negative 1.75, and I get my answer as 0.01. How many significant figures do we have? 1.75, so 3, okay. So I can say 178 molar, okay? So I told you guys up here, based on this equation right here, the concentration of the hydronium ion is the same thing as the concentration of nitric acid. So nitric acid concentration is 0.0178 molar. Okay, because it's a strong acid, you can do that direct conversion. Okay, now I'm looking at this. This is a pH. Let me make sure I did this correctly. 1.75, 10 power negative 1.75, because I don't know why my number, none of the numbers I have matches this. It should be as simple as that. Huh. Okay. I am thinking one of they have a typo here, but let me see. Because I'm looking at this and saying, I don't think this is. It's a pH. They didn't give us a pOH. And they just want the concentration of the solution. And I covered all my bases. But the number that looks the closest is this one here to my answer, right? Okay, let me click through everything. It says, no, you may have omitted a negative sign in the pH equation. Okay, let me see. We said 10 power 1.75. Oh, that's the number you get. This one here, no, exactly. You see how they go through all of that? That is impossible. Okay.
Even on the number, it says 0.18.
Right. They had me tripping. I'm sitting here thinking, what have I done wrong? Okay, yeah, very good. Very good observation. So, because I'm sitting here thinking, what have I done wrong? Okay, very good. So here, right? Yes, in their defense, sometimes they make mistakes. And when you're working on this, don't panic, okay? Don't be like me. Sometimes I show you what not to do. Because I'm looking at my steps and I'm like, I did everything correctly. Yeah. They're in their explanation, they have the right answer, but in the answer choices, they don't have the right answer. So our answer is right based on what they have down here. Sometimes I don't know what they must have rushed to do this. So the answer is 0.018. Right. Thank you for that. I'm sitting here thinking, what have I done? Okay. So what I just worked right here, bottom line, with the strong acid, depending on the number of H's, each H makes one hydronium, right? So if they give you the pH, do the inverse log of the pH to get H3O plus, and then whatever you have here equal the strong acid. Okay. Question number 7, because they're giving you Ka, communicates to you it's a weak acid. So let's compare question number 6 and question number 7. Question number 6 is a strong acid problem. So while we're here, I'm just going to let you know, most strong acid problems don't give you a Ka. Because when I was a student, that's the kind of question I have. It's like, okay, my test will not only be over strong acids or weak acids, it will be over both. When I'm looking at a question where all these questions, or a test where all these questions are mixed, how do I know? Question number 6 is a strong acid problem, and number 7 is a weak acid problem. Weak acids have Kas usually. Strong acids don't have Kas. But if they did, strong acid will have a very large Ka, like we said back somewhere here, right? Strong acids will have a very large Ka. What is a very large Ka? Where the exponent is like a positive number. You see how all of these have got negative numbers? I can look at this and say, based on these numbers here, oh, these are weak acids. How am I judging them as weak? The Ka is power, some number times 10 power negative 4, negative 4, negative 8, negative 10, they're all weak. If the Ka was some number times 10 power 4 times 10 power 4 times 10 power 8 times 10 power, if the exponents were positive, I'll be like, oh, they're strong. Okay. But if you're getting a little anxious, to ease your anxiety, the Kas of strong acids are not usually provided. Okay. Let me tell you a little story about my past. So this is me. I'm ashamed to say, okay, but this is the truth. So I'm going to tell you like I see it. Junior level, I'm in a P-Chem class. P-Chem, physical chemistry is the junior level class where we pick up where we left off in 1412. It's just like 1412, but it has calculus in it and more stuff and more physics and stuff. Anyway, I'm in that class, I'm in the exam, and I'm having an anxiety attack, and I've forgotten what's the strong acid. Yes, I'm telling you the truth. I'm like, I should know this. I believe I know this. What's the strong acid? What am I dealing with here? And I had a question like the one in number 6. So I'm like, I can't ask my teacher, sir. 4-year college teachers are not very friendly. Is this a strong acid? But I need some help. So what do I do? Okay. Professor, can I get the Ka for nitric acid? Yes, number 6. He looks at number 6 and he looks at me like, you don't need the Ka? I'm like, yes, it's a strong acid. Listen, he looks at me like, why do you need the Ka? I told you guys, recall is my worst skill. I understand logic, things that make sense. I knew that strong acids had large Kas and weak acids had small Kas. I noticed that in the questions, when the question had a Ka, it was a weak acid, but I have to ask my teacher to give me the answer I need without letting him know. Right? So he's looking at me like, what is she up to? And the other kids are, reading the exam, so you hear a lot of this. They're all going to question number 6. And then later on, after the exam is over, they're asking me, why were you asking for that? I was like, I forgot if it was a strong acid. Listen, you got to do what you got to do, right? Right, Rocio, you got to do what you got to do. My teachers, I was always asking these questions and like, why is this woman asking for this question? And I'm like, yeah, I needed that confirmation, because without knowing that, I was fixating on the question and it was making me second guess myself a lot. And it was just one of those things where I needed them to assure me I was doing the right thing, right? So we survived that. Listen, they still like me, so I guess I didn't completely mess up their relationship by asking them those questions. But yeah, so yes, so I did notice questions with weak acids tend to have Ka. That I was able to notice. So when he told me you don't need a Ka, I'm like, okay, this is a strong acid. Okay. Now that we've done the whole story, I tell you the story because I'm hoping to imprint this memory and this experience in your head, right? She told us that one story. Okay, number 7, we're told this time find pH. Okay, so this is going to be some number. We're given concentration of the aqueous benzoic acid. So the benzoic acid is usually, let's see, they didn't give us a formula. I don't need to write this out. Benzoic acid concentration, C6H5COOH. Yeah, that's the acid, of the benzoic acid. And we're given the concentration of this benzoic acid as 0.350 molar. They also gave us a Ka. I've already given you the whole story, how you know that now, because you're given the concentration, check, and the Ka, check. This is definitely a weak acid problem. Well, what do we do with weak acids? We don't do a direct, first of all, there's going to be, because we judge this as weak acid, we're going to have the following. Equilibrium equation. So in the place of the one-way equation I did up here, we're going to have an equilibrium. So in the equilibrium, you don't have 100% ionization, right? You only have about 5 to 7. It's a very weak acids have very low ionization. This percentage here is going to be very low, between 1 and 10, maybe even less than 1. So between 0 and 10. right? Very weak ionization. And then what else? We're going to have to use the ice table. Right. When they give you the Ka, most likely you got to use the ice table because it's a weak acid. We don't do direct ionization, no one-way arrow equilibrium equation. Okay, so for this part here, I'm going to write my acid as C6H5COOH. This would be my acid. So I'm starting with this part, plus water. I'm writing my equilibrium to give me C6H5COO minus AQ plus H3O plus. Okay, I know that it's a weak acid. How do I know it's a weak acid? They also gave me a Ka, right? So my Ka for this, I'm going to write this here real small, 6.5 times 10 power negative 5. Okay, right here. Hopefully you can see that. This number right there. Okay, so my equilibrium equation I wrote goes with that Ka, right? Now I have to draw my ice table. So my ice table right here. Right here, I, C, E, ergo the ice. Okay, so I'm working on this part next. You start with your initial concentrations, right? In molar, thank God the unit is right. So 0.350. Remember, we leave out the liquid part because the liquid part is liquid and it's not going to be in the equilibrium expression in the first place. Initially, there is no amount of this, no amount of this because nothing has happened. This is going to be molar. Okay, this is balanced, right? So you look at the coefficient, and the coefficient here is 1, 1, 1, 1. If it helps you out, you can say you multiply the coefficient by x. Remember, reactants are decreasing in concentration with time, so you're multiplying each coefficient by x, but then remember the products are increasing because they're being made while the reactants are being used. So in the terms of change, you will write here minus x for change for the acid, and the product you put plus x because products are being made, reactants are being consumed or used to make the product. Okay, equilibrium amounts, you add the two. We have 0.350 minus x. I'm leaving the m out. I'm writing out a space. X, I got x. Okay, after I'm done with my ice table, I know what comes next. Ice table means, part A, you have to have K expression, right? And then B, solve for x. Okay, so what's my K expression? My Ka expression Ka expression. Oh, this comes from the balanced equation, right? Ka is equal to 6 C6H5 C00 negative H3O positive over C6H5 COOH. Okay, remember we leave the water out. Okay, now this is an equilibrium expression, so you only put the equilibrium values in here. We have the actual Ka value, 6.5 times 10 power negative 5. So 6.5 times 10 power negative 5 equal the top numbers. These are the equilibrium numbers right here in terms of x. X times x divided by the bottom number, 0.350 minus x. Right? 0.350 minus x, that's in the bottom. Okay, let's see. I added those. Yeah, I want to make sure I'm doing this correctly. Okay, so now let's see. What do? We're trying to solve for x. So we can continue with this, but it appears to me that we might end up with a quadratic equation. We don't like quadratics, so let's check with the 5% rule. The rule that gives you a pass if you have feelings you're going to end up in the quadratic equation, right? This rule gives you a pass. Take your Ka, divide by your initial concentration of the acid, and multiply by 100. Do you get less than 5%? So what's my Ka? 6.5 times 10 power negative 5 divided by 0.350 times 100. Okay, open parentheses. 6.5 x. I said 6.5 and I wrote 0.5. 6.5 exponent negative 5 divided by 0.350 times 100. It's small. It passes. What does that do to my equation? It eliminates this minus x here. Only the variables added to a number, not the variables multiplied to a number or multiplied to each other. So only that x gets taken off. And now my math is simplified. Okay? If we can simplify chemistry math, we simplify. This and this gets multiplied, right? On the bottom here, we have 0.350. So now I'm going to solve for x. 6.5 exponent negative 5 to the right, close, times 0.350. This time I'm not going to forget this squared, because last time I forgot this squared. 2.275 times 10 power 1, 2, 3, 4, 5. Negative 5. Yeah. X squared. So find the square root of this number right here. And I'm getting x equal 0.00477. Okay. This is molar. Okay, so when I plug these back in the numbers back here, and I hope I did everything correctly. Added that, yeah, XX, subtracted that. I mean, it looks good from my end. I'm going to put these numbers back. So here's the thing. When you mix a benzoic acid with water, we have all four formulas present at equilibrium, right? Unlike the one-way reaction where you have no reactants and only products, here we have all formulas present at equilibrium. But what amount of each? for the benzoate ion, we have 0.00477. For this one here, molar, 0.00477. This is what I'm getting here. For this amount here, how much do we have left over? 0.350 minus the answer we got, 0.345. Okay, before I continue, I want to make it a point. Here's the thing. Acidity is not based, when we're measuring acidity, we're not measuring the original formula. Until I took Gen Chem 2, and so Gen Chem 2 in America, at home it was my high school chemistry class. Until I took this chapter here, I always assumed, because I was taught that way in the other chemistry classes, that we had introductory chemistry classes, I guess that's the equivalent here, that this formula here was the acid. It wasn't 100% incorrect, but when it comes to the ice table, we are not judging acidity by this formula. We're judging acidity by the H3O plus. That's technically acid molecule, not the formula. Okay? Are you guys clear on that? It's the H3O plus that's the judge of the acidity, not the original formula. So what I mean by that is, once I do all this math and I solve for this number, what I really solved for here was the H3O plus concentration. That's the important acid ion. This is the acid ion, not the formula that produced it. How do I defend my answer? Because at this point you can say defend your answer, and I will. When you're trying to figure out the pH of the acid, you're taking the pH, the negative log base 10 of just the H3O plus ion, not the original formula that made that ion. We're not using this number. If you use this number, you get it incorrect. You get it wrong. You use this number here. And this is one of those learning moments I had to come to as a student, because I had some preconceived misconceptions based on what I thought I heard as a student. And I just thought, well, this is the acid and this is the acid ion. When I'm trying to figure out the pH, I figure out the pH of the acid, that one. So what I will do at this point, I will put this number here, 0.345, in this formula here and get it wrong. And at some point I realized, no, the formula literally says pH negative log of H3O plus, not the formula of the original acid. So I have to pay attention to those numbers. So negative log. So you get what I'm saying? Can you skirt by with a superficial understanding of this stuff? Yeah, just enough. But can you get deeper and make sure that you really understand it? You can do that too, right? So here we are, negative log base 10 of the H3O plus concentration. Nothing else but that. Okay, so where was I? Negative. I have to get a log on my phone, on my computer calculator. 0.00477. This better be right or I'm calling somebody. I'll be like, why have you done this? Okay. I feel a little okay because acids tend to have a lower pH, right? Please be right, because if it's not right, I'm going to be calling somebody. Yay, there it is. Okay. Of course, their work is a lot neater. Let me try to make this bigger. Their, their work is a lot neater, but remember, they didn't even write the actual formula. They used a generic HA. Okay. So as I'm saying, even though I don't know if you guys are thinking the way I was thinking back in the days, that the HA is the acid because it is called the acid. There is something that's communicated. If you think anything like me, you understand what I'm saying. I used to think because we identify HA as the acid, when I'm figuring out the pH, what should go in here should be the number HA at equilibrium, not the number H3O plus, right? But the pH is calculated from the H3O plus because H3O plus is the true acidic ion. That's why even in the acid-base lab handout I gave you guys, you had to focus on expressing the acid by using the H3O plus. That lab was to kind of train you to associate H3O plus with the acidity. Did I hear something? Okay, thought I heard something. Okay, so H3O plus is the acid molecule. Anyway, there. Yes, we passed. Okay, let's see. You will approach this number 8 the same way, so I'm not going to work on that, right? Even though this is, the Ka is kind of big, but I did tell you, okay? So here's a defense. This is how you know this question is still a weak acid question. First of all, they gave you the Ka value, right? This number is not bigger than 1, okay? If you're not sure about that and in your head you're telling yourself, it's all relative anyways, how do I truly know in my heart? Okay, for you, my other defense is HClO2 one of the 6 strong acid. Let me scroll back up here. Scroll. No, HClO4 is one of the 6 strong acids. So since this is not in one of the 6 strong ones, by default is weak, you will use the same approach. Only the difference is, I'm telling you right now, times 10 power negative 2 Ka value, this will fail the 5% rule. And for this kind of question, quadratic equation all the way. Yeah. Okay. When you're working on these, I'm always trying to get an angle, you know? I'm not really a conspiracy theorist kind of person. I'm always angle. Is there an angle here? Is there a way? You can't see my face right now, but I'm stroking my chin. Is there a way? Right? So let me show you the way I'm talking about. Ka values that are some number times 10 power negative 5. If the concentration is about like this number right here, 0.3 something or something like that, this number tends to pass. You want to verify it, though. Don't gamble on that part. Just verify. Take Ka, divide by the number given to you. It tends to pass. If the number is like this, where the power is times 10 power negative 2, with that, it tends to fail. Okay? So you can just brace yourself and plan for a quadratic equation. This one here, you're doing percent ionization. Let me see. I never even got a chance to finish this one here, let alone do the next chapter. Well, that one was very, very recent, right? pH. This one here is similar to what we just did. Again, weak acid. Actually, this is not even a weak acid, but it's a salt of a weak acid. We didn't cover that, so don't even worry about that one here. Yeah, don't worry about that one. So what I'm going to do here is, this is similar to what we did. The only difference here is you're finding OH minus. So what I'm going to do here is, with this one here, I won't work the whole thing out. Not at all. What I'm going to do is just discuss what you do with the answer. So I won't know what the actual answer is, right? So here we're working on acetic acid solution. So let me do like what they did. I'll call my acetic acid HA. If you're working on this on the exam or homework and you don't know the formula of the acid, you can either find the formula of the acid or you can use HA is like X, the generic acid. Okay, this is my acid, AQ, plus water, H2O. And then, yeah, I just go ahead and work this one out. A minus AQ plus H3O plus. Because I feel like I could at least do 2 ice table problems. Okay, I have Ka here, which is 1.8 times 10 power negative 5. And they gave me the concentration of this 1.45, right, of the acid. They want me to get the percent ionization. Okay, I'm going to write this up here. Percent ionization formula is so similar to the 5% rule that sometimes I end up confusing the two. Percent ionization is saying what amount of the acid ionized compared to the original compound. So in other words, what's the H3O plus concentration over the original acid amount, and then multiply this by 100, which is similar to kind of to the 5% rule, right? Versus the 5% rule says take the Ka divided by the acid times 100. So I kind of confuse the two, but when I write it out, I'm less confused. So while I'm here, let me do the 5% rule because I went ahead and wrote this down. 1.8 times 10 power negative 5. I told you negative 5 with this number here will most likely pass, but I want to verify, right? No guessing if you can verify. Okay, let me check this real quick. Open parentheses, 1.8 exponent negative 5 to the right, close parentheses, divided by 1.45. Ha! It passes. Passes. Okay, so let me work this out real quick. Ignore that part, 0, 0. This is initial change equilibrium. Negative x, right, because it's 1, 1, 1, 1, plus x, add these two, 1.45 minus x, 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 okay. Ka is A minus H3O plus over HA. At equilibrium, put all the equilibrium numbers. I put here 1.85, oh, 1.8, no, 1.85. Brain focus, 1.8 times 10 power negative 5 equal, this is x times x over 1.5 minus x, okay? We said the 5% rule passes, so this minus x goes to 0. So essentially 1.45 times 1.8 times 10 power negative 5 gives me x squared, okay? So 1.45 times 1.8 exponent negative 5 to the right, close parentheses, and I end up with 0.0000261 equal x squared. Take the square root of that number and I get x equal 0.0051 molar. Okay, so remember the x that we care about here is this x. We care about this x here. This x is 0.0051 molar. I can go in and fill the other ones, but I don't care about them. All I care about is this one here, right? I was about to say pH. No, I care about this because this one here is the number I move on in my next formula. My percent ionization is going to be the concentration of H3O plus over the concentration of the original acid, which is going to be 0.0051 molar, times 100. What was the original acid? 1.45, right? I think it's 1.45. I'm kind of working fast. When I work fast, I increase errors. I hope I didn't make a lot of errors. Times 100. Okay. 0.35%. Man, remember, a strong acid is 100% ionized. That means all the molecules are broken apart. None of them. Like if you do a roll call, all the original acids are broken apart. This one is not even 1% ionized. It's a very small percent. 0.35. Yikes, this is a very weak acid. Okay, for that concentration, okay, let's see, please work. Yes, there. Okay, it's a very weak acid because remember, the percent ionization ties into the acid. The higher the percent ionization, stronger acid. Strong acids are close to 100% ionized. They do it 100. I'm trying to remain hip. Anyway, yeah. When they ionize 100%. Weak acid, they're called weak. This is not a derogatory term. They're just weak based on their ionization. They don't get to 100, right? Okay. Number 13. I wanted to do that one here. Number 13. So we're done with this. Number 13. Which compound forms an acidic solution when dissolved in water? Okay, so these are all, first of all, salts. How do I know salts? Salts are ionic compounds. If I can spell ionic compounds. And they are, how do you identify them? See, in chemistry, we're always judging. People are like, you judge. I'm like, that's what I do in my career. I need to turn that off right now. But we're always judging the molecules. So you have potassium, nitrite, metal, nonmetal, in that order. Most of the time, right? Calcium, nitrate, metal, polyatomic nonmetal. Next one, sodium chloride, ammonium chloride. What was the question again? Which will form an acidic solution when dissolved in water? Okay, so once again, one of them questions, right? Conceptual questions. These are all salts. So let's go back to the quick background of how we make salts. We're going to use the first definition of acid and base to define how a salt is made. According to Arrhenius, 2 R's, acid, as with base, these are the parents, and they make salt and water. Okay, this is kind of the background story that led to their formation. So we can view, in this context here, we don't care about the water. We're trying to look at the beginning, the origin of salt. Where does salt come from? So salt is the baby, the offspring, and the parents are acid and base. So what I did as a student, I know I have a wide imagination. I don't care if you make those judgments. I made it of myself. Since when you look at the acid and base interaction with litmus paper, when I was a student, I decided to make the mother the acid. Hey, just because it turns litmus paper pink. And then the base was the father. My teachers never knew this, okay? So for me, I was like, well, acids turn, and we had to memorize that stuff, right? So to kind of make this whole narrative in my head, acids turn litmus paper pink, bases turn litmus paper blue. Pink is in the society associated with females, blue male, so mother, father, and then the salt, right? For the most part, if the mother is a strong acid and the father is a strong base, right? Since their strength is assumed to be equal, they tend to make a baby or an offspring or salt that is neutral because both parents are strong, right? And then to kind of justify what I'm about to go into, I brought in my knowledge of genetics. I was taking chemistry while I was taking biology, right? So it's like having seeing a kid and you see their parent and you're like, this kid looks like both parents. How is that possible? Genetics. So both parents have equal strength and they both influence the kid equally, kid being the salt. If you have a strong acid combined with a weak base, let me write it a little smaller, then the strong parent dominates. You have acidic salt, right? The strong parent dominates. So it's like looking at them and saying, oh my goodness, your dad has strong genes. You look like a photocopy of your dad. You don't even look like your mom at all, right? Oh, sorry. In this context, my bad. The acid was the mother, right? You look just like your mom. You're like, oh, this is what they say online. My mini me. I'm like, genetics, strong acid, weak base situation, right? And then when you have weak acid plus strong base, it's hard to get the chemistry stuff to go viral. I don't. Nobody really cares about chemistry. I don't know why. Just nobody does. I can't be like, oh, you look just like your mother. This is a strong acid, weak base situation. They'll be like, what? Not to be like equilibrium. Nobody really cares. Just nobody cares. Basic salt. So I go with genetics. It's more acceptable. Okay. The strong parent influences the identity or the behavior of the offspring, where the offspring here is the salt. Okay. Now, when both parents are weak, it's complicated. It's complicated. So with this one here, when it gets complicated, we use experiments, right? Complicated. So you use experiments to help you sort through the complications. See? Like that. Okay. And then in the experiment, you end up using a table, and the table kind of illustrates to you which is stronger, which is weaker. Okay, back to the question. They want us to find out which one formed an acidic solution. So they want us to find this situation here where the acidic salt will form acidic solution. So we have to identify the parents, right? Okay. Now going back to the parents. Let's see. I said metal, not metal, right? The metallic portion of the salt comes from the base. Okay. So for example, in the first one, KNO2, this ionizes into K plus, right? NO2 minus. This K came from probably KOH. That's the base, right? And then the non-metallic portion, if I can spell correctly, of the salt comes from the acid, the mother. So this came from the acid, right? So this is kind of how I survived this section. The book has its own take on how they justify it. What I do to recreate the father or the base is I add OH. So if you notice what I did right here, I just added OH. And for my acid, to get this acid, guess what I did? Oh, I'm not following my own format. Hold on. This is my acid, right? Acid. All I did was I added H plus to get the mother. Okay. So we're going to do this for every one of us, and then we'll make a judgment. So starting with salt, let's call it salt A. Potassium nitrate. K plus NO2 minus. Add OH minus, and I get KOH. Add H plus, and I get HNO2. Then I have to judge, what kind of base is this? Strong base. What kind of acid is this? This is not one of the six. One of the six strong acids is HNO3, weak acid. So this is not our answer because this will give a basic salt. Okay, that's A. So we just said A did not qualify. Why did we disqualify it? It will give us a basic salt and basic solution. They said they want acidic. Okay, second one, calcium nitrate. Okay, break it apart into ions. Ionize this. Calcium 2 plus. Nitrate. We make 2, right? But each nitrate, I'm going to be adding hydrogen to it. So since there's 2 nitrates, I do this twice. And I end up with HNO3 2 times. And then calcium, since I have 2 positive, I have to add 2 hydroxides, right? Because I have to end up with a neutral compound. So I end up with calcium hydroxide. Man, this is bringing up 1411. Yeah. So what kind of base is this? I told you guys earlier, a metal with a hydroxide is a strong base. So once again, metal hydroxide, strong base. Yeah. Nitric acid, one of the strong acid. So technically, this forms a neutral solution because both parents are strong. Okay. Part C, sodium chloride. Once again, sodium ion, chloride ion. Add a OH here. Add a H plus here. There's only one positive ion, one negative, right? So I get NaOH. You're getting the trend here, right? Here I get HCl. Strong base, strong acid. Yeah, neutral salt. Just like that. The children can be explained by the parents. Well, if you think about salt as a child. Okay, finally, the last one. NH4Cl. This forms NH4 plus and then Cl minus. So here is where things get a little bit complicated, but anyway, here. You add H plus, you add OH minus, and we get NH4OH. This is not a metal hydroxide, right? It's a non-metal hydroxide. So this was mentioned at some point in the slides that ammonia bases are weak bases. Okay, and to kind of add a step further, this breaks down to form NH3 plus water, and this is the weak base they're talking about right here. So ammonia bases are weak bases. On the other hand, HCl continues to reign as a strong acid. I mean, by virtue of logic, since the first 3 were incorrect, the correct answer would have to be this one here, right? So ammonia bases are weak bases. Even if you add the OH here, this tends to break down. We learned this in 1411, that ammonium hydroxide is not very stable. It tends to break down to form NH3 and water. So what they're doing here is NH4 is formed from the conjugate acid of a weak base NH3 and the conjugate base of a strong acid Cl, so the solution is acidic. When I was in school, I heard what they were saying. I just knew my brain was not going to be able to reproduce what they were saying that way, right? And so this way helped me to remember it. And then since the questions they were asking me at this part wasn't to justify my answers, but to to give the answer. I was like, okay, I can use this logic and it works, right? Man, I've already gone over. Any questions about this? Okay, y'all are kind of quiet. So that was just chapter 16. This chapter 16 was long, and 17, well, 17 was 17. Let's kind of skim over that real quick. I know you guys have to go. Oops, I clicked on the wrong thing. This part right here. Oh no, I hope it didn't boot me out. Did it boot me out? Oh, okay. Self-assessment quiz, that's what I want. Okay, and then click here. Let's see what they have going on here. Oh, buffer. Huh. Okay. This is one of those questions where even though they have numbers, the question is not really about the numbers. Okay. So I'll cherry pick what questions I go over because as you can see, I'm already over by a good 10 minutes. None of you is saying anything. Okay, so chapter 17. Number 1, we're told we have a buffer. It helps to have the word buffer, but if they don't say you have a buffer, this is one of the ways you can tell you have a buffer. In a buffer, you tend to have the acid-base conjugate pair. Okay, remember the acid base or the conjugate, this is how they say it here. The conjugate acid base pair. So what we just learned, right? Buffers tend to have conjugate acid base pair, and in those questions, they tend to give you the concentration of the conjugate acid and the base. Okay, so when I'm looking at this question, if the word buffer was missing, I would see 0.100 molar NH4Cl and 0.100 molar NH3. Yeah, so I have to recognize these as conjugate acid base pair. How do I do that? First of all, I need to recognize this is a salt that breaks apart to form NH4 plus Cl minus. Remember, in this story here, Cl minus is just the father of the bride slash escort. It's just there to escort the ion that we really care about, NH4 plus. Okay. NH4 plus is being combined with NH3. So remember, these two are acid-base conjugate pair or conjugate acid-base pair. My book said it differently. I'm trying to learn how to say it in this book. Okay. Remember I told you guys before when you compare these two species here with the conjugate acid-base pair, the difference is either you have an extra hydrogen in the positive or you have less hydrogen in the positive. In this case here, going from left to right, you can see that there's one less hydrogen and one less positive charge. So this is definitely conjugate acid base pair. Okay, so this is definitely a buffer. So we're told in this buffer situation, when a small amount of hydrobromic acid is added to the buffer, which buffer component neutralizes the acid? Ooh, this is one of those conceptual problems. So in an acid-base pair of the buffer, remember you have the acid component. So in this case here, NH4 plus, this is classified as a weak acid, and then NH3 will be its conjugate base, one or the other, right? Weak acid conjugate base. Or if you decide to start with this would be the conjugate acid, and then, sorry, the acid and then the conjugate base. Sorry, the base and the conjugate acid. The bottom line is, since they wrote the NH4Cl first, I'm going to look at it this way. Okay, here's the thing. This is the acid, this is the base. They're saying when a small amount of hydrobromic acid is added. So this situation already exists where these two are mixed. They're already mixed. You're adding hydrobromic acid. So you're adding this HBr. HBr is also an acid. So which component, the acid or the base, will neutralize the hydrobromic acid? Remember, they're asking you about a neutralization reaction. Okay? So the neutralization reaction will happen between the hydrobromic acid and which of these two components? What do y'all think? Will the acid neutralize the other acid, or will the acid neutralize the base?
Acid will neutralize the base.
Yeah. Neutralization reaction by definition is acid-base reaction, right? So if this acid is being added, the base is the only one that can neutralize it. So let's see. Our base is this. Yay! Okay. When an acid is added, it has to react with the base component to generate more conjugate acid. Okay. Then here we have, oh, they want the pH of a buffer. Let me see what else we have. Similar to that. Similar to that. Which pair makes effective buffer? Okay. So what I'm gonna do, I'm gonna write here real quick the questions I'm gonna answer. I'm gonna answer effective buffer number 5. Let me skim over this real quick. The chapter does get complicated. I think KSP is not that bad. Number 15. Man, okay, I'm pushing it, y'all. I'm pushing it. Number 15. I think this question is simple enough. The conceptual ones are the ones that are a little more difficult. Right. We didn't cover everything in this chapter. I kind of summarized it and made it less difficult. Okay. And then number 2. Okay. So this is with the remaining time I have, which I really don't have because I'm actually boring time. I'm going to do number 2, number 5, number 15. Number 2, what is the pH of a buffer? So we did this before in the previous question, right? In the regular weak acid question. So skim over this real quick, right? What is the pH of a buffer? Number 2, they want us to calculate pH. pH will be some number. pH does not have a unit. What are we giving? We're giving formic acid HCH2CHO2. We're giving its concentration 0.120 molar. So right now, as I'm reading, I'm right here. And I'm giving potassium formate KCHO2 as 0.080 molar right there. And then formic acid, Ka, 1.8 times 10 power negative 4. Negative 4 may or may not work for 5% rule. I'm already thinking 5% rule, right? Okay, so because I have a Ka here, I'm thinking weak base. I'm sorry, weak acid, right? Ka, weak acid. Okay, but we're talking about a buffer. They said buffer, right? So at this point here, I actually want to go ahead and use the ice table to solve this. I'm going to write my buffer, since they have Ka here, I'm going to write my acid equilibrium first and then add the potassium formate, okay? This is my weak acid. I'm going to write HCHO2 plus water. And then this is my weak, what's it called? My weak acid situation. So I have to have equilibrium arrow. And then CHO2 plus H3O. Brain focus. H3O plus negative here, right? Here I've lost an H from here to here, and this is what I have. The Ka that goes with this is similar to the acetic acid one, but it's times 10 power negative 4. Okay. I have my initial, I have my change, I have my equilibrium. So since I'm dealing with a buffer, I'm going to write here B for buffer. I'm going to have 2 initial concentrations. One for this acid, which is going to be what? 0.120 molar. As usual, we ignore the water because the water is liquid. This is AQ, this is AQ, this is AQ. Okay? And then I'll have one for this one here. Where do I get this number? Please notice this formula. This is a salt. So when KCHO2 CHO2 gets in water, it breaks apart to form K plus and CH2O2 minus. This is completely gone. So whatever amount of this we had, which we had 0.080 molar, forms this amount here, 0.080 molar. So I write this number right here, 0.080 molar. Okay? Since I'm one of the person who's asking a lot of questions before we even got to the end, like my husband says, my thing is, if I look at an ice table, from the ice table, I can judge if the ice table is a buffer ice table or if the ice table is just a regular weak acid ice table. How can I judge? Buffer ice tables have got 2 starting concentration. Weak acid ice tables have 1 concentration, right? So if this was not here and the number was not given in the question, this would be a regular weak acid problem. Okay? I thought I heard something. Oh, I keep thinking I'm hearing things. Okay. But since I was given this number, which I had to put here, this automatically makes it a buffer problem. Okay. I wasn't given anything for the hydronium ion. Usually we're not. So this is going to be 0, like regular. Okay, 0 molar. Okay, just like before, we do our change in terms of x, 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 negative, negative, positive, positive, negative x, positive x, positive x, right? Then you add these, 0.120 minus x, 0.080 plus x, and then x. Okay, then we do the K expression. Ka equal, just like with the weak acid, CHO2 minus, I should erase this part here. It makes this formula look very weird. And then H3O plus over HCHO2 like that. Okay? Then over here, what do we have? At equilibrium, this number here is 0.080 plus x, right, for this number here, and then 0.120 minus x right here. And then we got Ka. What's the Ka number again? Oh, 1.8 times 10 power negative 4. This is the moment I've been waiting for. Is the 5% rule going to pass? Please pass to make our math easier. Okay, 5% rule. 1.8 times 10 power negative 4, and then 0.0. I'll try this number, the bigger number, times 100, right?
Okay. You got an app over your screen that popped up.
Oh no! Why are you trying to sell me stuff? Thank you. This is my. I'm not buying all this stuff, yo. I'm just looking. Okay, thank you. 1.8 exponent negative 4 to the right divided by 0.12 or 0.012 to the right times 100. Man, 1.5. Okay, let me make sure with the other number just to make sure it works out. 1.8 exponent negative 4 to the right divided by 0.08 times 100. Well, that one was better. Okay. Woo, 1.5. It still passes. It's still not 5%. That was close, y'all. That was close. Okay. How does that simplify our math? Once again, the variable added to the number, another one multiplies. So this becomes 0. This becomes 0. And our new math is now 1.8 times 10 power negative 4 equal 0.08 times x divided by 0.120. So let me make sure I did my math correctly. Is this 0.120? Oh, so this one here should have been 0.12. Hold on, let me make sure it passes. 1.8 exponent -4 divided by 0.12 times 100. Oh, it passes. Okay, either way. 0.12. Okay, so 0.12.08. I got my numbers correct. Okay, now I have to solve for x. To solve for x, I take 0.120 times 1.8 times 10 power -4. And then, of course, this will go on the bottom, right? So this will multiply here. This will go down here. So divide by 0.080, and that will give me x. Okay. So 0.120 times, open parentheses, 1.8 exponent -4 to the right, close parentheses, divide by 0.08. Okay, I'm getting x as 0.0027. 0.00027 molar. And this is going to be the x that goes in here, right? So we really care about the H3O plus. Most of the time, I recognize the part that we care about in the formula, not all the time, is this part here, the hydronium. So 0.00027 molar. Okay, you can fill in the rest over here. I'm not going to do that because of time. So what is the pH? This is the same thing as the H3O plus concentration, right? So pH is negative log base 10 of the H3O plus concentration, which is the same as this number. So say negative log base 10 of my answer, and I get a pH of 3.57 or 3.56 something. Okay. So I'm trying to see. I was working on question number, was it number 2? Wait, why do I feel like I'm in a different problem set? Oh, there, number 2, 3.57, right? So this is what I get, right? Now, the alternative method you can use is you can use Henderson-Hasselbalch equation. If you use that one, it's more straightforward, and they did do that one too. So you can use whichever is easier for you. pH is pKa plus log base over acid. And then you were given the Ka, right? So you take negative log of the Ka. So whichever works for you, use that. Remember, I'm just doing a review right now. You still have time between now and your exam, so you can go over this again. 1.8 times 10 power -4. Only in the buffers do you have more than one way to solve for this. And then base and acid, let's see. Our acid is going to be our weak acid, which is going to be our 0.12, 0.12, and then the base is going to be the 0.08 molar up here. So you can use either this method to get the same answer. That's what they use over there, and they end up with 3.57. You can use either this for buffer with 5% rule. So only the buffer situation do you have a choice of either using the ice table or using the Henderson-Hasselbalch equation, the one I call the HH equation. Okay, that's what they chose right here. Okay, I said I was going to work on 2. I got done with 2. Number 5. What is number 5? Oh, thank God it's conceptual. Woo! Okay. My brain is saying it's time for food. Okay, it says here, a buffer composed of a weak acid and its, okay, so that's the conjugate acid-base pair. So number 5, buffer is the acid and its conjugate base pair, right? So you can see from acid to the conjugate base, from this to this, you just lost a hydrogen and a positive charge. Okay. Which pair of concentration results in the most effective buffer? We want the most effective buffer, best buffer. Okay, somewhere in the notes, I don't want to go back in the notes because of time. They talked about concentration. They said if you want to have the best buffer, you want to have the highest concentration, right? So it's potent. It's like, if you have a headache and you have 50 milligrams of aspirin versus 100 milligrams, you want to take the one that's more potent if you want to get the headache gone quickly, right? So it has a great punch. And then second has to do with the amounts. So highest concentration, large amount, if that's possible. And then the other thing they talked about is approximately equal. Approximately equal acid base amounts, right? Because the acid will neutralize the base neutralizes the acid. You don't want to have a lopsided defense system. You want to have an even defense system. That way, if you have base, the acid can neutralize it. If you have acid, the base can neutralize it. You don't have a lopsided defense system. Okay. Now, the idea is you want to have these three scenarios if possible. So let's go through here and look at this. Which pair is the most effective? Okay, these are even, right? Even amounts of each. Okay. And these are even amounts of each. The middle ones are not even there. These are definitely very lopsided. So much of the acid here, not enough of the base. So much of the base here, not enough of the acid, right? But man, this is a tricky question. They're tricking you here. Okay, I'm just letting you know. That's my perspective. Here you have even amounts, but then you have a higher concentration. Here you have even amounts, but you have a lower concentration. And then here you have a lot. It would have been best if they had put 0.9. That would have been the excellent choice. What do y'all think we should pick?
50-50.
Let's try that one. Yeah. Okay. I mean, we're kind of gambling here, but they prefer it if you have even defense, right? This solution here, if the threat coming in is a base, it's ready. It has 0.90 molar worth of concentration to attack that base. If it's an acid, it's like, it will offer a weak defense, and then the buffer won't be very effective, right? It'll be like, I tried, we're out of solution, it's over, whatever, the end. Same thing here, right? Lopsided. So option B and C, you have lopsided defenses against that incoming threat. Right. So correct. The most effective buffers have high concentration of the acid and the conjugate base, and then they have equal concentration of the acid and the conjugate base, if possible. And of course, you want to have large amounts, which kind of goes with concentration too. They didn't bring that one in the equation or the question. The last one I was gonna work on here was the I forgot the number, was the number 15. Okay, let's scroll to that one, and then I'll let you guys go for real. For real. Oh, which compound is more soluble in an acidic solution than in a neutral solution? Okay, this is kind of like the parent situation, parent, strong parent, weak parent situation. But you see how when you cover the two chapters together, it's kind of like a sequel of the previous chapter. That's kind of how I see it. The deeper story, the stuff that's going on after the other stuff went on. Okay, so I'm going to end on this part here. Number 15. Okay. Which compound is more soluble in an acidic solution than a neutral solution? So, which compound? And if you notice, all of these compounds are salts, right? Which salt or compound is more soluble in acidic solution? So what I want to do here, y'all, is talk about before we even look at the compounds, what exactly, so we're comparing acidic solution, right? Acidic versus neutral. Neutral is not the one that we're examining here. There is something that's being added to the equation, so to say, by the acidic environment. So when we say acidic here translates into high amounts of H plus or H3O plus ions. Okay? Remember, H plus and H3O plus are the same thing. H3O plus is when H plus combines with water. But to make things simpler for us as we deal with this, I'm just going to focus on the H plus. Okay? I just think it's a lot neater. As high acid means H plus. Even if they say just acid, period, because the neutral doesn't have high acid, but if it's acidic, they mean you have extra H pluses than in a neutral, right? In a neutral solution, while we're here, the amount of H pluses are equal to the amount of OH minus. That's why it's called neutral. But in acidic, that means you have more H pluses than OH. Okay, if we have to resolve that. Okay, what does a lot of H pluses do to the first one? So we learned about these salts in the context of KSP. So BaF2 is a salt that is not soluble in water. Okay, we talked about this, and the context was solubility. So solubility is what we're looking at here. Solubility. BaF2 is a solid naturally in water. It ionizes to form Ba2 plus 2F minuses. So I'm just ionizing this according to the KSP equation, right? We have equilibrium here. We usually have a KSP value that goes with this. Okay. What else? Oh yeah, I have to recall the rule. Let me move this down. Sorry. I'm trying to get into this real quick before I recall the rule. The rule. Solubility. If a if an ion of a salt combines with H plus to form a weak acid or water. Oh, I said it a lot better today versus the last time I covered this. If an ion of a salt combines with H plus to form a weak acid or water, comma, solubility increases. Okay, this is the rule we are applying to judge which one will be more soluble. Okay, so apparently one of the ions, because I said if an ion, either this or this, will combine with the H plus. Ooh, that's where the H plus comes in. If it does form a weak acid or water, it forces the solubility to increase. So this is what we're going to be checking for both ions. Okay? Okay. This ties back to Le Chatelier's principle, where if we're moving to the right like this, we have increased solubility. Okay? And if we're moving left, we have decreased solubility. If you are a memorizer, your brain has the ability to take a picture of this, and if you're one of those, what's it called? You have those photographic, right, memories. You can take a picture of this and remember it. My brain doesn't work like that. My brain is like, what? No, logic. So I'm gonna explain it the way it makes sense to me. You see, the left side is the only one that has a solid. The side that is solid also has decreased solubility. The side that's aqueous has increased solubility. So if we're going to the side that has solid, you're decreasing solubility. If you're going to the side that has aqueous literally means soluble, right? So if we're going to the right side, we're going towards the side that favors solubility. If we're going to the left side, we're going to the side that doesn't favor solubility. That's how I remember. If you're photographic, take a picture in your brain. Okay, let's go ahead and do this. Examine each one. So Back again with our barium fluoride, solid. The good thing about these kind of equations, the left sides are always the solid part. Okay? Okay. Our environment is acidic, right? We said it was acidic. That means there's all these H ions surrounding it. The H ion or the proton is positive. It cannot interact with barium because positive doesn't attract positive. Positive goes after the negative. Like, yeah, negative right here. Opposites attract. So when the H, oh, people, why are you trying to get a hold of me? When H plus gets with F minus, what happens? They combine to form an acid. Okay, is this one of the strong acids? The list is way, way, way back somewhere. Okay, I had that list somewhere, the list of 6 strong acids back here. Look at all that chatter I can get from. I could have sworn this is what I'm looking at right now. Oh yeah, there. HF is not a strong acid, right? It's a weak acid. So you want to have the list of strong acids memorized. Don't be like me, asking the teacher for a Ka value. Don't be like me. I could not care about being embarrassing. I wanted a grade. I was shameless like that. So this is a weak acid. Oh, we said back here, if it forms a weak acid, solubility increases. Okay? So solubility increases. Oh, so BAF2 is the answer? What? Okay. Yeah. But let's see why the other ones weren't correct. Okay, let's see why the other ones weren't correct. And if you're asking, wait a minute, wait, I feel like we're memorizing. I want to understand why. Each H plus in the solution removes one F minus. When they're combining to form this, remember this HF is a weak acid, it's not going to break apart. These form strong relationship. Fluorine is one of those elements, it has some bad behavior, but in a weak acid, it forms a relationship with hydrogen and they're together for a very long time. When they get together, they don't break apart. So the hydrogen removes fluorine out of solution. Each hydrogen available removes fluorine. With time, it decreases this, forces the equilibrium to shift to the right. So the equilibrium has to shift to the right to make up for the lost fluoride ions. And then by shifting right, you get more of the soluble product. So solubility increases because it shifts right. Okay, what about CuCl? Let's ionize that real quick. This is a solid. Copper 2 plus, Cl minus. We got 2 of that. Did they just... Okay, maybe they mean copper 1. Okay, whatever. Copper positive, Cl minus. Let me try to follow what they're saying. Maybe they're saying that. Okay, so copper plus, Cl minus. Once again, the H goes after this. Well, when H plus gets with Cl minus, it forms a strong acid. The strong acid, as soon as it forms, it breaks apart and forms this. So it's almost like they never even got together. They don't stay together. This is one of those annulment situations. They didn't even, like, they got married and then they divorced on the way out of the church or the chapel. Like, yeah, they didn't even stay together, not even one day. They break apart immediately and they remain separate. So this one here, we have no change in solubility because solubility. H plus is not able to pull Cl out of solution. They can't even stay together. So issues in their relationship. AgI, solid, equilibrium. Again, Ag plus I negative, AQ, AQ. Can H plus poach or remove I minus from solution? Let's see what happens. H plus tries to get with I minus, another tumultuous relationship. Doesn't last, breaks apart. H plus and I minus remain separate. H plus failed to remove I minus from solution. So it's like nothing ever happened. No change in solubility. Okay. you know the trend. So if in this last situation here, we're dealing with lead with 2 bromines, what's going to happen? Same thing. H plus will fail. Nothing personal against H plus. This is all chemical behavior. It's not personal. It's chemical. I'm trying to make it. I'm trying to make this catchy phrase, but it's just not catchy. Nobody cares. It's okay. I try to console myself. One of these days, nah, it's not gonna happen. People just don't like chemistry like that. They're like, we're not all about that. I get it. I get it. I mean, it could be fun though if we all, I'm just saying. I'm just saying. Okay. Can H plus remove Br from a solution? Let's see. H plus tries to get with Br. Same thing happens. Forms a strong acid. They do not stay together. They remain separate. So therefore, conclusion. H plus fails to remove Br from solution. So once again, we get no change. And that's the end. It's kind of, I mean, to me, I'm just like, this is kind of a sad story, but all that is not being communicated here. This is just the stuff that goes on in my head. Okay. But you can see here, in the first scenario, that was the only time where hydrogen ion was able to remove fluoride ion from solution. In doing so, it forced the equilibrium to shift to the right according to the Chatelier's principle, thereby forcing the solubility to increase. In lab, let me tell you what happens in lab. In lab, if you have barium fluoride in a solution, it will be very milky, like a milkshake. And then you add acid to it and it turns clear. Bam. And that communicates this increased solubility. I mean, lab stuff is cool, but theory is like the stuff that explains what's going on. Anyway. Okay, guys, this is it. I know I've done a lot. Once I save this, you can go ahead and review this. And, but this is all I have for today. Any questions?
Thank you.
Okay, you're welcome. I'll see you guys on Wednesday. Okay, bye.